Well, good morning and welcome to this webinar, which is entitled Java at Speed. What we're going to be talking about today, as the title would suggest, is how we can improve the speed of Java applications, but without necessarily changing the Java code that you're using to run your particular application. What we'll be discussing is how we at Azul have made changes and have modified the JVM to produce our Xing JVM, and what that can do in terms of improving the way that your application works. So first of all, let's talk about what we really mean by speed, because obviously speed means different things to different people. What we need to understand is, are we fast in terms of our application? But as I say, there are a number of different ways that we can look at speed. The first of those is how fast we are in terms of rolling out new code. Now that in itself can be looked at in a couple of different ways. So how quickly can we roll out new iterations of our code? So we're using continuous delivery, continuous integration, that type of thing. But it's also from the point of view of when you roll out those new versions of your application code, how quickly do those versions of the code come up to the speed that they need to? We'll talk more about that later on. The second one is, are you fast when it matters? Yes, you may be fast in terms of response times for your application when you have a low load, but as the load changes, your response times may also change. And if you're not able to respond quickly enough as the load goes up, then you're not fast enough when it actually matters. This is something which affects a lot of applications where you have varying loads on the application depending on whether it's a market open, whether it's a particular day of the week or a particular day of the year, depending on what sort of things are actually going on. It can vary the load on your system a great deal. And how your system responds to that in terms of being able to meet that load is really about how fast your system is. And that's another way of looking at speed. And then another way is looking at how fast you are when you need to start using your application. If you take an example like when a market opens, so if you're running a financial service type application, when the market opens, you need your application to be running as fast as it needs to run at that point. And you don't need to think to yourself, okay, well, there's going to be some sort of warm-up period where the application comes up to speed once the market is open. You want it to run at full speed when the market opens. Otherwise, you may miss trades, you may lose money. But there are also other ways of looking at that ability to start at full speed if you're spinning up things like microservices. And again, we'll talk more about this as we go through. And then, of course, the other thing is understanding, are you reliably fast? So it's all well and good saying, well, okay, our system can run at a particular speed and we can support a particular load and we can do that. But if you have to go through a situation where your system will run for a while and then it needs to be restarted in order to continue being able to deal with that load, then that's not reliably fast. There are a lot of customers that I know of where they actually tune things to try and avoid having to restart their systems until after the market has closed. So again, if you're talking about financial service applications, you tune your system so you can run for a full trading day, and then after the trading day finishes, you can restart your application in order to reclaim space and run garbage collection and things like that. But again, we'll see how we can avoid these problems as we go through. One thing I would also like to add, which I should have done at the beginning, is if you do have questions, please feel free to add the questions through the question box that's part of the webinar. And at the end, I'll address the questions that people have. Now, again, talking about speed and what do we mean by fast, let's look at a graph. Simple graph of time versus speed. How quickly we can respond to something, how quickly we can do something that needs to be done by our application. And really what we're talking about here is this is our ideal graph. We want our speed to be constant. So we want to set the level at which our application wants to run, and then over time we want that speed to be absolutely constant. We don't want to have to worry about warming up. We don't want to have to worry about dips in performance as load changes. We simply want our speed to be absolutely constant over time. Now, how does this fit in terms of the Java world? Now, the important thing with Java is that what we're dealing with is a managed environment. Now, that's a very good thing because the JVM, Java Virtual Machine, does a lot of work for us in terms of our application so that we don't have to write a lot of extra code when we're developing our applications. Types of things I'm talking about there are things like the use of bytecodes. So we don't need to think to ourselves, what particular platform are we targeting? Are we targeting an Intel architecture? Are we targeting an ARM architecture, PowerPC architecture, and so on? Are we running on a Microsoft operating system? Are we running on Linux? Are we running on something else? All of these things are abstracted by the JVM for us, this wonderful write once, run anywhere idea that we've had for a long, long time in Java. And even beyond that, the idea of memory management being handled by the virtual machine. So the fact that you can allocate objects and you simply say, I want a new instance of a string, Java Virtual Machine will allocate space for that, and it will keep track of where that string is being used, and when it's no longer being used, it will reclaim the space automatically for you through garbage collection and allow you to reuse that space for other objects. This is all very good stuff, but what it means from the point of view of your performance is it introduces non-deterministic behavior to your application. What I mean by that is that the garbage collector will run at times when your application code is running, and because of the way that most garbage collectors run, it will introduce pauses. It will need to stop your application threads in order to tidy up, in order to reclaim space, and so on. And this can change things in terms of the way that the speed of our application works. Now, from a point of view of compilation, we have bytecodes. So when we start running our application, the JVM will use those bytecodes as an intermediate form between the source code that we had in our application and the actual instructions that need to be executed on whichever platform we're running on. What will happen is at the beginning of our application, we will start using interpretation of those bytecodes. So each bytecode will be taken by the virtual machine, converted into the necessary binary instructions for the architecture, and executed. And every time we need to use bytecodes, it will happen again and again. Now that's very inefficient because we have to do the same work repeatedly. So what happens is as the application starts to run, we do profiling. This is the hotspot idea, adaptive compilation. So as we notice through the JVM that we have particular hotspots in our code, which could be a loop that we're executing many, many times, profiling will identify the methods that are being called and the code that's being executed in that loop. And then that will be compiled into native instructions, which can be cached and can then be reused when the loop is executed again. That way we don't have to keep reinterpreting the bytecodes every time. We can use our chunk of compiled code and we can then run that more efficiently. But further than that, what will happen is that we will then optimize that code. So we will use information and profiling about how the code is working to determine what we can do to improve things even further. And if we look at this graph here, what we're seeing is that the yellow part is where we start off 100% of the time running interpreted code. As we start to compile our code, we go through this profiling, the initial compiling phase, and we see the green phase of the graph. And then as we move into totally optimized code, where all of the code that we're executing has been compiled into native instructions and has been fully optimized, we'll see the blue section where we're running 100% compiled code and optimized code. What we'll also see in this graph is a number of spikes. And what those spikes tell us is that the compiler is making certain assumptions about what the code is doing, and it will optimize based on those assumptions. But the problem is that at some point, those assumptions will be wrong. It's perfectly valid, and I'll talk more about this a little bit later on as to how it works. But something will change in the way that the code is running, and suddenly the compiler will need to say, oh, okay, I made an assumption about how this code was going to work. I got that assumption wrong. We'll switch back to interpreted mode until we can re-optimize that if we need to. So this is where we're seeing these spikes. This is what's called de-optimization. If we look at the way response time works, then we're going to see a graph like this. And again, we're seeing the yellow part, which is where we're seeing the interpreted code. We're seeing the green part, which is where we have our profiling and initial compilation, and then the blue part, which is the optimized code. From a response time, obviously when we're using interpreted bytecodes, it's slower, so it will take longer to respond to requests from our clients. As we move into the compiled and then optimized phase, the effect that has will become less and less. So we'll see that the colored part of the graph drops down until we have a steady state where the impact of the execution of the code is minimized by optimizing the code that's compiled. However, what we also see are these red spikes that happen regularly, and those spikes which reduce the response or increase the response time, reduce the speed of our system, increasing response time, are due to other effects. And this is typically when we see garbage collection. So the garbage collector has to pause the application threads, and by pausing it, it increases the response time, decreases our speed. Right. So let's look again at our ideal speed graph. What we want is a flat line, continuous from the beginning, full speed, and not changing. But clearly that's not what we've seen in terms of the way that the Java speed graph or response time graph works. If we flip our graph around, so we're actually looking at speed rather than response time, we'll see something like this. So again, we start off with interpreted mode where the speed is lower. So we start off low speed, then we gradually move up as we compile our code, and then we optimize it, and we'll see that we reach a level which is 100% our full speed. And then again, we'll see certain dips in our graph. Some of those will be due to de-optimizations where the compiler has to change its assumptions about how the code is working. And some of those spikes, especially when we get to a steady state, will be the ones that are being caused by garbage collection. But as we can see, this looks very different to the graph that we have in terms of our ideal. It's not a nice flat line at 100% right from the very beginning. So what I'd like to do now is I would like to run a quick poll for those of you who are on the webinar. And the question that I'd like to ask is about how much time do you spend on tuning your code for performance? And I've got 4 answers to this. Hopefully you can see the poll, because I can't see the poll at the moment. So hopefully I'll give you a few seconds to respond to the poll if you can see it. I'm hoping you can. And then what we'll do is we will close the poll, and I'm just going to have to. Okay, so I can see the results. There we go. Okay, that's good. So interesting. So what we're seeing here is that the results of the poll, there's 15% spend a lot of time looking at almost every line of code, and 85% of you spend some of your time doing this. So it seems that people spend a lot of time doing work in terms of the tuning of their code. So what can we do to improve that? What can we do to help you, rather than having to look at all of your code and thinking to yourself, right, I need to tune this, I need to make it run faster. How can we eliminate some of those problems? This is what we do with Xing. Xing is our JVM product, and we take the OpenJDK source code, so we're using exactly the same basis for our JVM as other people who create JDKs and JVMs do, but then we change it. And there are really 3 things that we have in terms of the features that we try to address the problems. Now, clearly what we're looking for is this ideal graph where we have a flat line constant from the beginning. And so to address that, we have a set of a product which is called Ready Now. This is built into Xing. It's not an optional feature. It's already there. You don't have to pay any extra for it. It's part of the package. And what we can do with that is shift our graph so that we don't have the warm-up issue that we see here, where we start off slow and then we gradually get to a point where we're running fast. We have another thing which is C4, that's our garbage collector. And this is designed to eliminate the dips in speed that we see caused by a traditional garbage collector, because it's pausing the application threads in order to do its work. And then the newest thing that we have, which is Falcon, which is our JIT compiler, is designed to take the optimum level of performance that we have and shift that up so that we get a better level of performance when we actually run our application. So what we're doing is taking that graph where we've got the different colors representing the different parts of it and making it into this darker blue one, where we start up much, much more quickly and we reach a higher level of performance and we don't get those dips when the garbage collector kicks in. Let's talk more about how this actually works then. So we'll start with Falcon. Now, Falcon is a very new set of technologies that we've introduced in Xing. It's only been as part of our default product for a few months now. And we decided to call it Falcon because Falcon is the fastest animal in the world. As it dives, it's actually the fastest animal in the world. So we thought, we want fast, we'll have a fast animal as our code name for this. Now, Falcon is based on an open source project called LLVM. LLVM has been around for quite a long time, and it's a project which is designed to help people who are writing compilers. And it's designed to address all the needs of compiler writers. So we're not talking just about the Java way of doing compilation in terms of adaptive compilation inside the JVM. It's much more about how compilers work, like GCC, standard static type of compilers. But there's lots of different pieces to LLVM that have been developed to help people who are creating compilers. So we looked at LLVM and we thought this seems like a good set of technologies and it seems like a good idea for using that. And what we did was we thought, right, we'll bring LLVM technologies into Xing and we'll replace the C2 JIT compiler that we've had in Xing for a long time. If you look at most JVMs, they have two JIT compilers. OpenJDK, they're called C1 and C2, so client and server. The idea of C1 is it has a faster warm-up time, but a lower optimum level of performance. C2 has a slower warm-up time, but a higher level of optimum performance. So we thought, right, we want to replace C2, we want to get the absolute optimum level of performance. And what we effectively did was say, okay, let's use LLVM, but we need to do some work in terms of adapting that to work in the managed environment of the JVM. As I've said, the JVM does a lot of things for us. And so we had to take the LLVM code. We then had to look at it in terms of how does it deal with garbage collection? How does it work in conjunction with safe points? How does it deal with application stalls? What do we need to do in terms of de-optimizations? Because that's not something that you typically deal with in a static compiler. How do we deal with code replacement? How do we deal with the dynamic nature of Java? Because we have dynamic class loading in Java. So we did a lot of work on that. And what we then did was we said, okay, we've done all this work. It's an open source project. We will now push those changes back into the open source project. So we're very good open source residents. We like to help open source projects. So all of the work that we did, we pushed back. We didn't keep it to ourselves. We've made it available to other people who want to use LLVM. Why we chose LLVM? This is a question I do get asked a number of times. And there's really kind of four reasons why we decided on LLVM. One is it's mature technology. The project was started 17 years ago, so it was 2000 when it actually started. So there's been a lot of work put into this. A lot of people have looked at how it could actually work. Different ideas have been applied to it and so on. Also, from a technical perspective, we felt that it produced nice code. So we like the code that it produces, and we thought that's the kind of thing we want. It has a lot of tooling available around it because it's designed for compilers. There's other tools that help with development, help with understanding things, help with debugging, and so on. And just from a technical perspective, we thought it made a lot of sense. One of the key things is the fact that it's very modular in its approach. So you can very easily add new modules. And this meant that when we wanted to be able to enhance Falcon in the future, using LLVM, it would be much easier to include new modules with new ideas, new optimizations. The other thing about it is simply the number of people who are working on this. As I said, it's an open source project, and there are a lot of big names from companies that are helping to develop LLVM. If you look at the kind of areas where you need expertise, people like Intel, people like AMD, people like ARM, understand how the processors work at the lowest possible level. So they're able to bring that expertise to the project and add the necessary code to make the compiled code work in the most optimum way on those architectures. And then if you move a little bit higher up, there's people like Microsoft, there's people like Cray, there's people like Sony, Apple, and so on, who understand the operating system level of things. And so they can, again, add their expertise, add the necessary code, and make the project work in the best possible way. So this was really the reasoning behind using LLVM. Now, let's just talk a little bit about modern servers, because we need to understand how modern servers work and what they can provide to us in order to understand what we can do to improve the way that our code works using the JIT compiler in the JVM. What I've got here is sort of a short history of the Intel architecture, if you look at things like the Xeon architecture. And we've been through a number of iterations from this. If we go back to Sandy Bridge, which is a while ago, this was a new set of technologies which introduced a thing called AVX. And this was about enabling vectorization of code. And what I mean by that is the ability to use single instruction, multiple data, SIMD. What that means is that we can take, if we have a large number of pieces of data that we're trying to process, rather than using a single instruction to process each individual piece of data, so single instruction, single data, we can apply one instruction to multiple pieces of data simultaneously. AVX used 128 bits for the registers that could hold the data. So if we were using a 32-bit integer, for example, or a 32-bit floating number, then we could have 4 of those represented at the same time. That way the vectorization could do an instruction on 4 pieces of data simultaneously as one operation, as one clock cycle. In the Haswell architecture, AVX2 was introduced. That doubled the size of the registers, so we moved to a 256-bit register, and so we could then do 8 simultaneous pieces of data with one operation. And in the Skylake architecture that's just coming out, that's being moved up to AVX 512. They seem to have changed the numbering scheme, so now it's 512, which indicates the number of bits in the register. So again, that doubles the number of pieces of data that can be operated on simultaneously with a single instruction. Obviously, cores and core counts have gone up and things like that. If you're running on a modern server, you're probably going to be running on a Broadwell, maybe a Haswell, but this is the kind of thing that you're going to be running on if you're using modern hardware in your data center. Now, what I'm going to do is I'm going to look at some machine code. Now, that might sound a bit scary, but it's very useful to understand a little bit about what actually happens in terms of what we can do to optimize things. I'm not going to spend too long on this, and I'm not going to go into enormous detail on this. So don't worry if you're not a hardcore assembler fan. I'll keep it fairly lightweight from that point of view. What we have in Xing is a tool called ZVision. And ZVision is really about profiling. So great, we can profile our code. We can see what percentage of time we're spending in a particular method, and we can see how the system is running. That on its own doesn't really buy you much. There's a lot of tools out there that will profile your code. But in this case, what we're doing is running some sort of benchmark, and we can see that there's a percentage of time spent in different methods. But then what we can do is we can click on those methods and we can actually see what the code is that's being executed by the JVM in terms of the compilation and then being handed to the processor itself. And if we click on one of those particular methods, we'll see a lot of information about the instructions for that particular platform that are being executed. Now, again, I don't want to go into enormous detail on this because this is really just about highlighting how we can optimize things. But if we zoom in on one particular part of that, let's have a look at the idea of executing a loop. So if we want to execute a loop, this is a simple piece of Java code that we might have. So we have an array of integers, primitive ints, and what we want to do is add them all up. So we'll write a very simple piece of code where we have a sum, we then use a for loop, we iterate over the array, and we add all the things together. This is a simple piece of code, and if you look at the typical sort of JIT compilers that are available today, they will be able to vectorize that using the basic vectorizing instructions that you have in modern hardware architectures. That's all good. Great. But it's a very simple example. If we make that example a little bit more complicated, where what we're going to do now is we're going to take two arrays and we're going to add the elements from the second array to the elements of the first array, but only if the element in the second array is even, then we have a slightly more complex piece of code. So we're very good in terms of checking that we don't have a difference in length. So we'll make sure that we have the same length for our arrays. And then we'll have our loop, but this time we're going to execute an if statement to test whether we have an even number. If we have an even number, we'll add that to the equivalent element in the first array. The problem with this is that in terms of vectorization, this is rather complicated, and JIT compilers are not able to use vectorization for that in its simplest form. The compiler needs to understand more about the more modern architectures. And this is talking about more AVX2 rather than AVX. So if we look at the code that will be generated by this, again, we see a lot of assembler, but we don't need to worry about all the details of that. What we can do is we can zoom in on part of this. And this is generated by a typical JIT compiler. What we'll see is that there are two elements being processed per iteration of our loop. So if we zoom in, you'll see there are two blocks of code there where there's a move statement where it brings in the value. There's a test to see whether it's an even number. If it's not an even number, if it's odd, then there's a jump statement which will jump past the next instruction, which is the one to add the two elements together. Great. So it's doing what we need it to do. And there has been some optimization because it's doing a little bit of what's called a loop unrolling, so that it does executes two operations on the data, or processes two elements of our array for each iteration of the loop. Great. That's a little bit of an optimization, but it's not really a huge optimization. And certainly from the point of view of using a vector, that's not going to help us at all. What we then need to do is look at the code that we could generate, and this is the code generated by Falcon on a Broadwell chip. So the Falcon compiler, JIT compiler, understands how the vectorization instructions work on the Broadwell processor, and one of the reasons it does that is because Intel contributed code to LLVM, which we used, so we got that bit for free, if you like. We didn't have to do a huge amount of work in terms of the code generation. What we needed to do was take the Java code and make it or turn it into the right form so that the back-end compiler could then generate this type of instruction. What we'll see is in here that we're vectorizing it. It might appear that there's a lot more instructions here in our loop, but we're actually able to do a lot more work in terms of what's going on. So using Falcon, what we'll see is there are, and I've highlighted here, there are six instructions that are being used to process a set of data. Now, because we're using vectorization and we're using a 256-bit register, what we can do is we can do 8 32-bit values in each stripe, and there are 4 stripes here that we're able to do. So we're actually doing, in effect, loop unrolling. So we're doing 4 executions on the data at the same time. So we have 8 values in our register 4 times. So we're actually doing 32 elements per iteration. And that's compared to the 2 that we were doing with the more naive code. The other thing that's really nice about this is that because we're able to do this vectorization, and this uses the very low-level support within the CPU, what we see is that if you take something like a 2.5 gigahertz processor, so we got up with a 2.6, something like that, gigahertz processor, the effective processing that we get here is equivalent to about 9 billion instructions or operations per second. And that's because it's doing about 2.5 billion reads, about 2.5 billion writes, 2 billion adds, and 2 billion ifs, all at the same time. So it's able to do those all in 1 second. Because the chip architecture is able to overlap these things, we can take advantage of that through the vectorization software, and we can get better performance out of that. So this is the kind of example of how Falcon, as a compiler, can generate much better code and give you much better performance in this type of application. Now, the other thing that we need to look at is how we work with speculative compilation. So I said that the compiler will make certain assumptions about what your code is doing. And this is one of the really interesting things, certainly to me, about how Java works. Often when I talk to people about Java, and I've been talking about Java for many years, they say, well, Java's slow because of the fact that it uses bytecodes and they have to be interpreted, and even with the JIT compiler it's still slower. Wouldn't it be nice if we could just take Java code and we could compile it into native instructions straight away? And yes, I mean, that's certainly possible. There's no reason why you can't do that. And in fact, there is work going on in the OpenJDK project to provide an ahead of time compiler, AOT compiler, where you will take Java code, and rather than generating bytecodes, you can compile it into native instructions for a particular platform. However, that isn't necessarily the best answer, as we will see, because what a JIT compiler can do is it can actually make optimizations that you can't do in a static compiler. And the reason it can do that is because it knows exactly what is going on when your application is running. Let's look at a couple of examples. So the first of these is what we call the untaken path example. Now, here's a rather convoluted and slightly, well, it's an example that we've created to demonstrate how this will work. What we can see is that we've got a method called compute magnitude. We pass a value to that, and then we have to test to see if the value is greater than 10. If it is, we have to compute the bias based on the value. If it's 10 or less, then the bias is always going to be 1. And then in order to return the value that we've computed, we return the base 10 logarithm of the bias plus 99. Okay, slightly strange example, but it helps to highlight exactly what the JIT compiler can do. Let's assume in this particular piece of code that the value we're passing is very unlikely to be more than 10. That's a very rare situation where something strange has happened, and we don't normally expect that to happen. But in our code, we have to take into account that it might happen. So we write our code to say that if the value is greater than 10, we'll compute the bias, and then we'll return the log 10. Problem is that for most of the time, the value is always going to be 10 or less. So what we'll see is that it's always going to be setting bias to 1 and then returning math.log10 of 1 plus 99. At this point, the JIT compiler can do that. So the JIT compiler can monitor things, it can profile, and it can say, well, val has up until now been 10 or less. So we can actually change that, and we can say, right, let's take the bit of code, the path that we always go through on this, and we'll compile for that. So the effective code that we're going to compile is to say, compute the magnitude, and we'll say if the value is greater than 10, because we still have to have a situation where we deal with that, we will do a thing called an uncommon trap. So we'll hope that that never happens, because so far we've never seen a value of greater than 10. So we'll hope that that continues to never happen. But if it does, we need to deal with that. So what we'll do is we'll do an uncommon trap, which will then take the code we've compiled and revert back to interpreting, so it uses the exact code that we have above, so it deals with it correctly. But because we know that most of the time this hasn't happened, we'll simply take the code in the top red box and we'll say, okay, well, we're always setting bias to 1, and then we're always generating the log base 10 of 100, which is 2. So let's not bother doing any of that. Let's simply return 2 every time, unless the value is greater than 10, at which point we do the trap. This is a speculative optimization. We're optimizing based on what we know so far. But if we get a place where value is greater than 10, we have to then unwind that code. We have to de-optimize. So this is where we see those spikes in our graph where we have to change things because the speculative optimization wasn't correct. Another example is an implicit null check. Now, if you look at how we access some field or an array in Java, we'll do it like this. We'll say x equals foo.x. So we're taking the value of x internally in foo and assigning it to x. But of course, if foo is null, we can't reference through it, so we get a null pointer exception. The code that's really generated is what we see here. So it's effectively, if foo equals null, throw a new null pointer exception, otherwise assign the value of foo.x to x, which is all good. So at this point, we could write that code ourselves, but it's actually down to the compiler to do it for us. So we don't have to make that null check every time. But the compiler can hope that we don't pass it a null. So we can hope that we never have to deal with a null pointer exception, which, let's face it, that's what we hope for in our code anyway. But again, because the compiler is able to deal with this, it can use the lower level functionality that's available in the operating system and in the hardware to enable it to optimize this. So rather than actually putting in an explicit test to see whether foo is null, and if it is, to throw that null pointer exception, what it'll do is it'll use the memory management system of the chip to say, if you try to reference through a null, we'll get a segmentation violation. We can then catch that as a signal, and we can do what needs to be done in terms of throwing that null pointer exception. So we can eliminate, if you like, the null pointer explicit test that we would have to introduce in our compiled code and let the hardware deal with that. So that is faster if no nulls are encountered. The other thing is how we can deal with inlining, even without final. And again, this is where people think that AOT, ahead of time compilation, can make their code faster, but this isn't necessarily the case. Let's look at this. So if we have a class called animal, and that has an encapsulated value field called color, and in terms of that color, we have a method to access it. So we have an accessor method, get color, and that just returns the color. Great. This is all good object-oriented code. So we have encapsulated our value and we have a specific method to encapsulate it. But that isn't necessarily great for performance, because if we want to get the value of color, we have to go through a method call. And so there's overhead in terms of all of the work that needs to be done for that. Really what we would like to do is simply reference the color value associated with the animal object without calling the method. Now we could do that by making color public and then just referencing animal.color and do it that way, but that's not what we want to do in terms of object orientation. So what we can do is we can let the compiler do that for us. So the compiler, remember, understands exactly what is loaded, it understands exactly what is being run in our application as it's working. So now what we can do is we can say, let's treat the getColor method as if it's just inlined. So we can say, we just want the color value associated with the animal. This will work so long as no class that inherits from animal overrides the getColor method. This is why static compilation can't make this kind of optimization, because static compilation can't guarantee that there won't be a class that overrides that method. So it must generate the necessary method call code for that. So if there is an overridden method, that particular method gets called. The JIT compiler understands exactly which classes are loaded and exactly which methods are being used, which methods are overridden, and it can do class hierarchy analysis. Class hierarchy analysis looks at what classes are being used and how the methods are in there, and it can determine that even though the getColor method is not final, there isn't one that overrides it. So for our cat, our dog, whatever animal we have, there isn't an overridden method, so we can just use the code that's equivalent to accessing the field as if it was a public field rather than through the method call. Obviously, if we had something like a chameleon where we needed to override the method, then the compiler would need to do the class hierarchy analysis, and it would see that there was a different method being used, and so it wouldn't make this optimization. But again, this is what it can do to improve the efficiency of our code. So as I say, we can deal with that exactly the same way. Class hierarchy analysis. This is actually one of the things which means that Java does run more quickly than you might expect, because we're not having to do method calls every time you do a field access through either a get method, an accessor method, or a mutator method. Let's talk a little bit about de-optimization. So we saw this graph earlier on where we saw that what was happening is we're compiling, we're optimizing, but we see these spikes. And as I said, these spikes are where de-optimization happens because the code that's being used is changing. And so the assumptions that the compiler makes change. So if we were to have a value that was greater than 10 in our earlier example, this is where we'd see a de-optimization. The thing with de-optimization is adaptive compilation is adaptive, as you'd expect. And so when it comes to dealing with this, you might think that micro benchmarking is a black art. You might think that writing effective benchmarking code is very, very difficult to actually represent what you're trying to do and not confuse the compiler. So is the art of warm-up. And this is one of the things that we see people doing with their applications. So what they want to do is that they want to run the code long enough to get to the point where everything has been optimized. Okay, but we know that de-optimizations can occur at any time because the code can change. So often those de-optimizations will occur after you think your code is warmed up. Many potential causes of this, as we'll see. So what will happen sometimes is if people are using, again, let's take a trading system as an example. So what they want to do is use a trading system, and they want to have the trading system run as fast as possible from when the market opens. What they'll do is they will try to warm up that application before the market opens. So what they'll do is they'll say, let's take 20,000 fake messages, run that through the system, get it to process those messages, and it'll warm up. So it'll understand what the code is being used to process those messages, and then the JIT compiler will take that code, it will optimize it, it will do what it needs to do. Great. And then when the system runs, we'll see it running as fast as it can at market open. However, the problem is that what you're dealing with is fake messages. In the case of a trading system, you're not actually going to be running real trades because the market hasn't opened. You don't want to push the trades from your system into like the actual trading system. So there will be an element of fakeness about what you're actually doing. The compiler will optimize based on the fakeness that you're actually doing with your messages. And when you actually run the system, you'll find that these de-optimizations happen because when you run the real system, you actually start doing the trades, things are different to the way they were before, and you'll start getting de-optimizations. This is a problem. So what we see is the idea that we take our application, we start it slow in interpreted mode, we run it through our fake processing of our messages, but then when the market opens, we start running real messages, and lo and behold, the optimizations happen, and suddenly the speed drops down a bit. Some of the optimizations will be valid, so we won't drop the speed completely, and we'll be able to pick up quite quickly, but we will see de-optimizations kicking in when the market opens. So in terms of how we want things to work, how things actually work is that we start slow, but we learn fast. So the compiler identifies the hotspots. It does other things like lazy loading, initialization. So this is the thing that happens as the application starts to run, and if we want our flat speed graph, we need to get past. Then we do aggressive optimization for all the common cases, and we get to our optimum level of performance. If we then restart that, or if we need to start with a different set of data when the market opens and doing different operations, then we'll revert to slower code through the de-optimizations. And then we bring back to full speed again. So this is how things work. This is our warm-up, where we start learning which methods need to be compiled, which bits of code need to be compiled, what classes need to be loaded, what initialization needs to be taken care of, and so on, and how we do our optimization. And then the de-optimization is when we have to temporarily revert to the idea of executing in interpreted mode rather than compiled mode. So what we have is this situation. What we actually want is our flat graph. We want no slow operations, no slow trades. We want everything to run at top speed right from the very beginning. How can we solve this problem? So what we do is we have this thing called ready now. And ready now, part of Xing, logs the optimization information as the program is running. So we'll look at what the JIT compiler is doing, and we'll say, okay, what decisions, what statistics is it saving, is it using, and we'll record all of these optimizations as a log. And then we'll get it to the point where you have a real running system, production system running with real trades, and we can see exactly what is going on in terms of the optimizations that are being used by your code. Then, when you start up your application, what you can then do is use that log to provide information to the JIT compiler, so that it has the same information it had in a real running instance of the application, and it can use that to optimize based on the reality of what's going to happen when you do actually open the market. We prime the JVM with that information, we apply the optimizations, and then we can also build a workflow around that. So we can actually say, right, you can monitor that, and you can see which optimizations have been applied. You can see if some optimizations haven't been applied, why they haven't been applied. You can actually see what's happening as the system starts to use the information from the log file. So again, if we look at what we see typically is when we start the load on the system in the real load, we see these de-optimizations, we see the fact that we get slower performance because of the fact that we're reverting to interpreted mode. So we're seeing those de-optimizations, which is not good. What we want to do is avoid those de-optimizations, and we can do that using ready now. So we load the log file, as I say, and then the compiler can use that as information rather than having to learn it over time. It's fed the information it needs straight away. It can take those optimizations, and we can then see, right, we've got the information we need, and we can go through warm-up, be fast from the start, and then we can load. So rather than doing that warm-up, we actually load at the beginning, and we get our flat graph where we've got optimum speed right from the very beginning, or at least very, very close to the beginning. So what we want to do is start fast and stay fast, and with confidence as well. So the important thing here is that we need to ensure that the code actually executes the way we want it to. So again, going back to the graph that we had before, what we're doing is we're saying, okay, ready now shifts the graph to enable us to put those optimizations in very, very early and avoid this whole warm-up phase. Falcon shifts the level up because we're able to take advantage of some better optimizations. C4 is where we eliminate the pauses associated with garbage collection. These are the dips that we were seeing in our graph earlier on. So if we talk a little bit about C4 just for a few moments, about how that improves things. What's really about is, as I said, eliminating the pauses associated with garbage collection. Garbage collection typically, if it has to move objects around, it needs to pause the application threads so that you get consistent data. You don't want to be trying to write to an object if it's being moved, because you might write to the old place when that particular data has been already copied. So keeping that data consistent is very important. C4 solves that problem. So what we see here is a simple visual summary. So this is an application that we did a test on. And again, this is now not looking at speed, this is looking at latency. So what we're seeing is the spikes where the garbage collection is happening. So the red graph that we see on the left, we're seeing spikes where you have pauses for the garbage collector to move objects around, to do its work, tidy up, and so on. The graph on the right is what happens with Xing. So we see very, very flat graph. We see no issues in terms of big spikes associated with garbage collection. Now, let's talk a little bit about garbage collection tuning, because this is something which, again, is a real black art, and you need to find people who really understand how to do garbage collection tuning to get the best possible performance out of your application. Garbage collection tuning is notoriously hard. So if I let's look at a couple of examples. So we've got two examples of these are real world applications where these are the command line options that we use to start them up. We look at the one at the top, that's setting a heap size of 12 gigabytes. The one at the bottom is setting a heap size of 8 gigabytes. Okay, so they're reasonably similar. They're in the same order of magnitude. Top one has 14 flags. The bottom one has 17 flags. So there's a lot of different things going on here, and they're very different flags. But also, if we highlight just one of those particular flags, the survivor ratio. So the top one, we've set the survivor ratio to be 128. In the bottom one, the survivor ratio is set to 2. Now, that's 2 orders of magnitude different. Now, how do you know? Should I set it to 128? Should I set it to 2? Should I set it somewhere in between? Things like that are very, very difficult to know. And it's very hard to profile and to understand exactly what's going on in your application to see which of those values you should be using. There are many flags. I mean, I remember doing talks about the way that the JVM worked in the past and counting up that I think in JDK 7 there was something like 700 command line flags. Now, all of them weren't related to garbage collection, but there are a lot of flags that you can use for garbage collection on the standard OpenJDK version. Right, how do we tune Xing? Now, what I'm going to say is you have to forget everything you've learned about tuning garbage collection in the past. You have to learn a completely new way to tune your garbage collection. Now, I know that might sound like a bit of a problem, but it's actually really simple. Because what you do is you simply say, let's set the heap size. So we'll set the maximum heap size to be, in this case, we'll set it to 40 gigabytes. And we'll run our application. Our application will run the way we want it to. Okay, how are we going to tune this? Well, all we do is we reduce the heap size. What we'll do is we'll reduce the heap size until we get to a point where the response time of our application is not what we want. Then we can move it back up again, and that's it. So all we simply say is, right, tune your heap size until you get to the point at which you're meeting your service level agreement, and then leave it. We do have a couple of extra command line options that you can use. They're quite esoteric, and we tend to only use those where people are very, very focused on absolutely the last possible millisecond or microsecond of latency, and we need to use those things. But typically for an application using Xing, all you do is set the heap size, and the rest of it is dealt with by the garbage collector. Here's a graph which we can generate showing the effect that the different parts of the garbage collector have and the different parts of Xing have. Now, I won't go through this in detail, but you can see there's a lot of different information there. It's fairly flat in terms of the different aspects. So you've got things around new generation garbage collection, you've got old generation garbage collection, and so on. You might look at that and go, well, there's a lot of pauses in there, and it's quite busy there, isn't it? But what you need to do is you need to look at the scale of the graph. So the top of that graph, right at the very top, is 1 millisecond. So what we're looking at here is typically nothing. There's a few spikes that go to up to about 45 microseconds, I should say, not milliseconds, 45 microseconds, but most of it's around the sort of 35 to 40 microseconds. Now, for most applications, that is going to be really background noise. It's not going to be something that will affect your application. In fact, you'll find the operating system will have bigger impact on your application than garbage collection will. So this is the kind of thing that you will see. Service levels. So the important thing is what you want to do is avoid having to restart your application in order to meet service levels. So what we can see here is a typical kind of graph that you might plot where you're looking at percentiles. You will have a service level agreement that says we want our system to respond within 5 milliseconds 90% of the time. Between 90% and 99.9% of the time, we want it to respond within 10 milliseconds. And above 99.9% of the time, we want it to respond within 20 milliseconds. And what you can then do is you can plot graphs based on how your system responds with a particular load. So we can see here we've got a hotspot running with 15,000 transactions a second, 10,000, 5,000, 1,000 transactions per second. And in terms of matching that particular service level agreement, it all sort of hits it about 5K, although there are definitely places where it falls outside of that, and it will match it at 1K, 1,000 transactions per second. So you could probably push that to something like 3, maybe 4,000 transactions per second and meet your service level agreement. It's a bit difficult to see with Xing because it's just a flat line at the bottom there. And so 15,000, 10,000, 5,000, 1,000, all pretty much on top of each other. And it's well within the service level agreement. So you don't need to worry about that. Just to talk about a particular example of a particular customer that we had, I'm going to have a warning here. Your results, your mileage may vary. So we're not saying that everybody's going to get results as good as this, but this is just an example of a real world customer. So this was video advertising, and what they had was a Cassandra cluster. So this is a very common thing that people have. So they're using 6 AWS instances of a particular size. They had a split in terms of read and writes 80-20, and they were using quorum consistency across the 6 elements of their cluster. And they had 6 client machines sending requests co-located with the same machines. Their service level agreement was 20 milliseconds for 99.9% of the time, 50 milliseconds for 99.29 or 49s, and 100 milliseconds for 99.998%. So rather than 5 nines, it's 4 nines and an 8, just because of the way that things worked with the AWS instances. Using Hotspot with the G1 compiler, or G1 garbage collector, I should say, they could maintain 4,000 transactions per second before they breached that service level agreement. When they used Xing, they were able to hit 21,000 transactions per second before they breached the service level agreement. What that tells me, and should tell you, is that with Xing, you can run over 5 times as many transactions per second on that set of hardware as you can with using Hotspot and G1. That equates to saving money because you can either use less instances or you can use smaller instances, but if you need a particular level of transactions per second at a particular service level agreement, what you're talking about there is a very easy to equate saving in terms of hardware costs when you're using either your own hardware or the cloud. So the answer to that is really quod erat demonstratum, or quite easily done. Right, so the idea, as I said, going back to our speed graph, just to finish off, is that we have these 3 things in Xing. The idea of Ready Now is to push the envelope so that we can shift away from using the warm-up period, away from de-optimizations as much as possible. We have Falcon, which can take the code and compile it and optimize it to a level which pushes the envelope further up. And then we have C4, which is our garbage collector, which eliminates the pauses as we go through. So the idea is to start fast using Ready Now, to go fast using Falcon, and to stay fast using C4. So that's pretty much on. I've got literally a couple of minutes left. A couple of things that I would like to say before I look for some questions is that if you're interested in understanding more about Xing, you can try it free for 30 days. So if you go to azul.com/Xing trial, that will take you to a place where you can download Xing for free. You can try it on your application. You can run it. It is a drop-in replacement in terms of the Java code, so you don't need to worry about changing any of your code. You can take exactly the same setup, replace it with Xing JVM, simply redirect your Java home or where your Java virtual machine is, and it will run exactly the same. I've also created a survey about this particular webinar, so if you have a couple of minutes, and it literally will only take a couple of minutes to complete it, I'm always interested to know if this kind of information is useful to people. If you thought there was too much information, so there's 6 questions. You don't even need to answer all 6, and there's really kind of 4 questions there. And you can find that at bit.ly/Xing speed, all in capitals. So with that, I'm just going to see if we have some questions. So let's see where the questions here. Oh, right. 450 microseconds. Yes. Yeah, you're right. Sorry, that was not 45 microseconds. That was 450 microseconds. I still get de-optimizations despite reading out. Could you explain how to use the compile F command file? Yeah, I mean, obviously, so the question here is about you still get de-optimizations using ready now. The reality is that yes, we can do so much in terms of recording the steady state of an application and the optimizations that are being used, but there are still going to be situations where you might get the optimizations that will affect your code. What I would do is I'll probably deal with this one offline, because I think that I can't actually go through the idea of using the all of the parts of ready now at the moment. So what I'll do is I'll take a note of that, and I will get back to you about that so that we can discuss how that can be used. So that is pretty much on the hour. So I hope this has been useful for you during the oh, hang on, I've got one more collection. Collected optimizations become useless, and given that presumably when the code changes, previously collected optimizations become useless. And given that fake trade data will optimize the wrong things, how to use ready now when releasing new versions to production? Aha, yes, I will answer this question, because this is quite interesting. So what you can do is, if you have, let's say you have a, we'll take a microservice as an example, because that's a very common thing at the moment. What will happen is you will have services that you will spin up using code. Okay, so you spin those services up. You will take, you will use ready now to build a profile of that, and then you can record it, and you can use it when you start up those new instances of the microservices. When you want to deploy a new one, what you do is you deploy a single instance of that new microservice version. You spin that up, and then you let that run parallel to your existing ones, and you build a profile of that. Then you can use that profile to spin up new instances at the best possible speed using the optimizations for that new version of the code. So yes, that is something that can definitely be done with ready now. So you can use that kind of approach. And then one last question: if C4 garbage collector does not pause our application, does it mean that we will be using more memory as it is not being freed? No, definitely not. The way C4 works is, rather than simply holding on to all of memory, it still does exactly the same things that a garbage collector will do. So it does compaction, it does reclaiming the memory, but it does it concurrently with your application threads. And the way that it does that is by intercepting all reads to objects, so that you guarantee that the object reference you get is going to be the correct one. So we allow application threads to run whilst we are compacting, whilst we are doing the collection. So that's the effect that we have with C4. It eliminates the problem of garbage collection. It doesn't increase the amount of memory. You can, in fact, you can actually, in many cases, get less memory usage by doing it this way. Okay, so I'm now going to, because I'm a little bit over the hour, so thank you very much. I hope that has been useful.